This section is all about approximating the values of definite integrals using simple geometric shapes. So we've already seen this in your first calculus class using a Riemann sum to approximate the area underneath the function. So let's warm up with a Riemann sum. We wish to approximate the area underneath the function square root 1 plus x to the 4. So I'm going to give myself just a rough shape of what this graph looks like. It's going to be something that looks like that. Doesn't have to be perfect. And I want to evaluate the integral, or the area underneath this function, over the interval between 0 and, let's say, 2 is right there. So I want to use 4 rectangles. So I'm going to take my interval, b minus a, and divide it by the number of rectangles I'm trying to squeeze in there. So 2 minus 0 over 4 gives me 2 over 4. Each rectangle will have a width of 1/2. So I'll move to the right, to a half, to 1, to 3 over 2. And this is how I will build my 4 rectangles. It doesn't specify left hand or right hand, so I'm going to use a left hand Riemann sum. So my function at 0 gives me a 0 height. My function at 1/2 gives me this rectangle. My function at 1 gives me this rectangle. And my last rectangle looks something like this. So the area between 0 and 2 underneath this function can be approximated by the sums of the areas of these rectangles. So I've got base times heights. Let's think this first rectangle. The first rectangle has a base of a 1/2, and it has a height given to me by the function value, right, whatever the function was at 0. So I'll just say f at 0. In fact, let me change colors here. This rectangle is right there. And then we'll add to that the area of the next rectangle. This rectangle has an area of 1/2 as its base times its height, which was the function value at this point, 1/2. And now if we look for the area of this rectangle, we have a base of 1/2 and a height given to us by the function value at this point, which is f of 1. And finally, our last rectangle, again, has a base of 1/2 and a height given to me by the function value at 3/2. So all of our rectangles have the same base. We can pull out that 1/2, and effectively, we're just adding the function values at 0, 1/2, 1, and 3/2. So if you plug 0 into your function, you get a 1. If you plug a 1/2 into your function, you get about 1.0308. It's okay to pass that to a calculator because at this point we are approximating. F of 1 turns out to be about 1.4142, and f at 3/2 or 1.5 is 2.4622. So when the algebra clears the room, we have an area about 2.9536. So this doesn't really belong in Calculus 2 notes. This is a Calculus 1 problem, but it's just going to lead us into the idea of approximating integrals using nice to compute areas.